container with most water solution. Let's start by clearly understanding the problem. We have several vertical lines represented by an integer array, where each integer indicates the height of a line. Our task is to identify two lines that combine with the x-axis to form a container storing the maximum amount of water. The water contained between two lines is restricted by the shorter height. Therefore, to calculate the water stored, we would take the height of the shortest line between the two, multiplied by the distance between their positions. Here's an example. Given heights 1, 8, 6, 2, 5, 4, 8, 3, 7, we attain the maximum water container from the vertical lines at positions 1 and 8. The height of the container is limited by the shortest of these two, which is 7, and the container extends for 7 units, resulting in an area of 49. Now let's focus on the optimal way to solve this problem to ensure the most efficient execution. One of the well-known techniques is the two-pointer approach. We begin by initializing 2 pointers at the two ends of the array, the left pointer at the first elements and the right pointer at the last. These pointers represent potential boundaries for our water container. At each step, we compute the width as the difference between the right and left pointers and the height, which is limited by the shorter line at the pointers. Using these, we calculate the area of the container. If the area is larger than the previous maximum, we update the maximum area. Finally, we move the pointer that refers to the shorter line, since the height of the container is limited by the shorter line, hoping to find a taller line inward that could potentially result in a larger container area. Testing our solution thoroughly is very important, ensuring its correctness and performance across various scenarios. Let's begin by testing the main example provided, ensuring it returns the expected output of 49. Additionally, let's test simpler cases, for instance, where the array has only two elements, 1, 1, expecting the output to be 1. Now let's check some edge cases. We test with increasing line heights, 1, 2, 3, 4, 5, 6, 7, 8, where we observe that the optimal container area is 16. Similarly, we test decreasing line heights 8, 7, 6, 5, 4, 3, 2, 1, where again the maximum area is 16. These tests validate that our two-pointer approach works efficiently and correctly, regardless of whether the height array is increasing, decreasing, or unordered. Lastly, it is vital to look at the efficiency of our solution. Analyzing time complexity, we notice that the two-pointers approach ensures we traverse through our array only once, since the left and right pointers both move inward without overlapping. Thus, the time complexity is O(n), which means it scales linearly with input size. On the other hand, let's consider the space complexity. We do not have any additional data structures like lists or dictionaries that grow with input. Our solution only uses a few variables. Since no additional space is used relative to the size of the input, and only a constant number of variables are employed within the solution, our space complexity is O(1). These complexities indicate an efficient solution suitable for handling large cases within the specified constraints of the problem. Great work! You've learned the robust, efficient two-pointer solution to solve the container with most water problem. Remember, understanding techniques like the two-pointer method helps in solving many similar algorithmic challenges efficiently.